Chapter 7 Mass Wasting. Welcome to mass wasting, or in other words, landslides. So remember I said that climate change is affecting all the hazards that we cover for the rest of the course? That includes landslides. How might climate change be affecting the frequency and magnitude of the landslide hazard? If you want to share your thoughts, totally email me. If you don't have any thoughts on it yet, keep thinking about it as we go through the chapter. This first image is of a landslide that happened in Bingham Copper Mine in April of 2013, located near Salt Lake City, Utah. No one was hurt. The debris flowed over 3/4 of a mile, moving enough sediment to fill all of New York's Central Park with 64 feet of dirt, according to Fox News. The slip plain was a fault line. The spring thaws and rain exacerbated the situation. Years later, the mine is still digging out and evaluating safety precautions. What a wonderful mess. 7.1 An Introduction to Landslides. Mass wasting is a rapid downslope movement of rock or soil as a coherent mass, which includes earth flows, rock falls, and avalanches. They are described collectively as landslides and are very related to water. The awesome picture to the right is of mass movement in a lake with a boat. The scene is in China. I wonder what the people in the boat are thinking. Are they scared and/or amazed? Or does this happen so often here that it's just another day in the life of Chinese boat people? Mass movement moves mass downhill or downslope. All slopes are constantly evolving and materials are always in motion downslope. There are two basic types of slopes. You have slopes composed of high cliff or free face with a talus slope at the bottom. Or you have slopes with a convex slope, i.e., meaning curved out section, followed by a straight slope and ending with a concave slope, i.e., a curved in section. I'll show you. Top left picture. Hard, strong rock like granite. Doesn't like to get sloppy. You have a cliff instead with a free face and a talus slope at the bottom, which is composed of rockfall deposits. The picture on the top right is a real-life example. Free face, talus pile, knocked over trees. On the bottom left, we have a slope comprised of relatively soft, weak rock. Yes, the rock is still pretty hard and strong compared to my hand, but for a rock, it is soft and weak. Examples might include highly weathered sandstone or shale. This slope is gentle and stable enough to have some soil and is composed of three segments mentioned before: a convex slope, a straight slope, and a concave slope. These segments are labeled on two different slopes in the image on the bottom right. Can you identify all the different slope segments on the lighter colored hill? Sure you can. Prove it to yourself. We will next be going through many types of landslides and other downslope movements. Here's my summary graph to kind of orient you. You'll be seeing this graph again later in the discussion, but let's take an initial look now. On the left, we have movement, and on the right, we have material. Under material, we have rock and soil. Under movement, we have rotational and translational. Rotational means that there is a bit of a curve to the downslip plane, which rotates the material a bit. Translational means that the slip plane was more flat, so the material just moves downslope, like a straight slide on a playground. And, as you can imagine, some mass movement has both rotational and translational movement, which makes it complex. So rotational movement produces slumps. Translational movement produces all the rest: falls, slides, slips, creep, flows, and avalanches. Let's go through a ton of examples. A slump is rock or soil sliding along a curved slip plane, which produces slump blocks, often with backward rotation. Hey, rotational movement. Generally highly deformed internally, so no more nice layers as depicted in the cartoon at the top right. But you can see the curved slip plane and the slump scarps, the abrupt breaks in the slope surface. If the material slumping is primarily rock, then it is a rock slump. If the material is primarily soil, it is a soil slump. If it is not primarily one type of material, but has primarily rotational movement with nice slump scarps, it is just called a slump. Image on the bottom left is another cartoon on slumping that also points out the toe of the slump at the bottom of the landslide. And the bottom right image is a real slump, where you can just see the top portion of the slump scarps. That's it for rotational movement. Falls are translational movement. Falling is the free fall of earth material. You can have rock falls and soil falls, or debris fall, where debris is just weathered material, usually a mixture of rock, soil, and other earth materials. The image on the bottom left is a cartoon of a rock fall, with the falling rock and the talus slope, and a road, with no cars, fortunately. I bet the sign is a useful mitigation strategy. Watch for rock. The image on the right is a real rock fall. See the cliff where the rock fell off recently? The newer talus slope? Obviously, this cliff face has been demonstrating classic rock falls for quite a while. Next type of landslide is a slide. Sliding is the movement of material as a coherent block. It is a sudden, rapid slide of bedrock and/or soil along planes of weakness. For rock slides, these planes of weakness are often sedimentary bedding planes and metamorphic foliation planes. Metamorphic foliation planes are layers of weakness that form in the rock as it is heated and squished. The new minerals that form will grow in directions that are influenced by the direction of the stress the rock is under as it is squished. This directivity of the new mineral growth can cause planes of weakness in the rock, which later can form planes of slippage. Sedimentary bedding planes are from when sediments were deposited before they were lithified, i.e. turned into rock. Sometimes a bunch of sand is deposited, and then maybe some limestone, and then back to some shale, and perhaps there were time gaps between the deposition of different sediment layers. These changes in rock type and time gaps actually leave lines in sedimentary rocks called bedding planes. These bedding planes are also often planes of weakness in the rock. These bedding planes all begin mostly horizontal, but may become angled due to tectonic forces, moving rocks into mountains and such. We have an example of bedding planes in the picture on the right. These bedding planes have an angle similar to the slope angle. When the bedding planes slope out from or along the hillside like this, they are sometimes called daylight beds, because they end where you can see them in the daylight, as opposed to underground where you can't see them, even in the daylight. Anyway, you can see how the slope seems to love to slide down these planes of weakness. If you can't see it in the real picture, there is a helpful cartoon on the left illustrating a rock slide along a slip plane that is also a sedimentary bedding plane. If the material is not primarily rock, the slide is called a soil slide, or soil slip, or debris slide, or earth slide. Planes of weakness often involve the regolith bedrock boundary, which is a fancy way of saying the boundary between the less weathered bedrock below and the more weathered material above, such as soil. This layer also corresponds to a change in permeability, usually decrease, meaning that water has been percolating into the ground relatively quickly, but then meets bedrock and can't percolate down as quickly as it could before. So the regolith bedrock boundary can get very soggy, and this will exacerbate slipping. The two images show soil slips. See how the one on the right looks like a toupee that just slipped down and you could glue it back in place? Soil slip. Moving on to flows. The movement of unconsolidated material. We are going to go from slowest to fastest. The slowest is creep. Creep is very slow flowage, on the order of millimeters per year. Think tectonic movement slow. This mass movement tilts poles and trees. Very common and very easy to identify. And a fun word to say. Look at that creep on the hillside. I wonder if those homeowners know about the creep in their backyard, etc. As you can see, the possibilities for nerdy geology puns are endless. So on to images. The cartoon. We have the curved tree trunks. Why do they curve? Trees like to grow up, but they are slowly being tilted sideways. So by combining sideways tilt with upward growth that occurs simultaneously and slowly, you get a curve. In contrast, fence posts and utility posts are not growing, just being tilted. Creep will slowly and relentlessly tilt everything down slope, but it won't be creeping down slow at the same speed everywhere. Why? Probably due to the heterogeneity of the soil composition and soil moisture content. These slight differences in rate of creep will also cause the soil ripples you may notice in the top right image. And you can totally see the tilted fence posts and curved tree trunks in the bottom right image, right? Now on to flows. A flow is a movement of unconsolidated material. An earth flow is slow to rapid. An earth flow is a downslope movement of soil which has been saturated with water to the extent that the debris moves as a fluid. It generally remains covered by a blanket of vegetation, and typically a steep scarp is developed where the moving debris has pulled away from the upper slope. In addition, a hummocky lobe forms at the toe or front of the earth flow. The image on the right is a nice example of an earth flow. Can you see the typical earth flow features? Identify the vegetation on the flow. See the steep scarp at the top of the hummocky toe at the bottom? Oh, and the hummocky toe at the bottom. Other flows include debris flows and mud flows. These are relatively rapid, 5 to 80 kilometers per hour. The difference between a debris flow and a mud flow is as follows. A debris flow contains particles that are up to boulder-sized, supported in sediment water slurry. A mud flow is a debris mixed with water with a high proportion of mud. Basically, mud flows have more mud. Okay, so the image below, is it a mud flow or a debris flow? Based on the picture alone, I say it looks like a mud flow.